Okay, let's begin. So, how's that quiz? The first proofreading quiz. No, it didn't go well. People shaking their head before I even asked the question. What was so tough about it? What about the first part where I asked you about negations? You guys thinking it okay?
Require a bit of thought.
Huh?
Require a bit of thought.
The negations, yeah. What about this one? I'm interested to see if anyone figured this one out. One, D. This one's actually easy. So this is quiz 4. I said there exists X such that P of X implies Q of X. Right. So the negation of this was what?
For every X, there.
Of course, for all X, that's the easy part.
For every X, P of X and not Q.
Right. P of X and not Q of X. I actually had you prove that use a true tip to prove that on a previous quiz. That this is the negation of that. That was one of the conclusions you had to make. Right? So I actually compared these 3 statements and you're supposed to say, oh, this one is the negation of that one and these 2 are actually equivalent. Right? That was the answer. The answers for all the quizzes are up. The quiz you just took, I just put the answers up on the website, by the way. So yeah, that one. The other ones I would assume you would have gotten. For example, what was like 1A for all X, P of X, or Q of X? What's the negation of that?
For some X.
Yeah.
There exists X such that
Not P and not Q.
not P and not Q. Right, so you're applying De Morgan's laws while negating the quantifier. Okay. How about the first proof? Like so I have 3n plus 7 is odd for every integer n implies that 4n plus 17 is even. Yeah?
Is it vacuous?
It's vacuous, yeah. True vacuously. Right, so you asked me about that book. It's true vacuously. This statement is actually false. What was your mistake? Did you realize what your mistake was?
If n is
Yeah.
I was just trying to prove everything,
Right, but so he came to me during the quiz and he asked the question, well, is this really true? Because, for example, if I plug in n equals 8 here, I get this is odd. But this is also odd, so obviously something is amiss. So the thing is here, what you actually did was you forgot this part. Has to be true for every n, right? Missing that word every actually changes the whole thing. It's actually not true that it's odd for every n. For example, if I plug in n equals 1, then it's not odd. And then that would be irrelevant, right? So the fact that it's for every n, so yeah, you can plug in a few n's where it doesn't work, but that's not what I said. It has to be true for every n.
so when you put them, just put true values.
Yeah, I wrote, in the solutions I wrote it down like this. Since 3n plus 7 is odd for all n in Z is false, right? And I even put an example, n equals 1, right? If I plug in n equals 1, this is actually even, right? We have the claim is true accuracy. Yeah, so I even put a small space and they're like, you shouldn't be working too hard here. It's actually easier than you think. The first part is false, so the overall statement is true. There was essentially nothing to prove. Just note that this statement is a false statement. It's not always odd.
I just assumed that one of them was going to be a vacuous proof.
Like one of them has to, yeah, he's definitely going to throw in one of these after. Okay, yeah.
For the top, What if, let's say for the first one, instead of putting P of X and negate Q of X, what if we just did negate P of X and Q of X?
Just negate, just write this.
Yeah, that's what I think.
This time around, I'll give you the point, but it's actually important that you know this. Right? When we get to proof by contradiction, you'll see why it's important that you know this formulation of the negation. Because when you're actually trying to prove something, then you're like, what is the negation of that, right? To actually use this in a proof, it's sort of weird how you think about it. Thinking about it as the and of two statements is actually going to be a lot easier for you. Yeah. So, I don't want to do, well, we have a lot more examples coming in. What about A and B are odd? Implies A and C are odd.
Oh, shoot. You scared me for a second.
Oh no, I put C instead of B. Okay, A and C are odd. Implies AB plus BC is even for all integers B. So, if that's the thing, how did you do this one?
Oh, really? Is that what you said? Shoot.
Well, direct proof is nicer, so if you at least assume A and C are odd, then you're off to a great start. Okay, so then what?
A equals 2k plus 1. C is 2j or 2l plus 1.
Okay, that's not the direction I went with it, but let's run with that. So 2k plus 1, C equals 2l plus 1. Okay, so for k, l, and z. All right, then what did you say? So 2bk plus b, and this guy is, and bc would be 2bl plus b, okay? And so when you add them, ab plus bc, you get 2bk plus b plus 2bl plus b equals 2 times bk plus bl plus b. Yep, very straightforward way to do it. So if you did that, you would have gotten it correct. I would expect most people to do that on the solutions. I did a different way. And this one should be Let's not do that. You'll see the answers anyway. But that one was more or less straightforward. What about the bonus? Because am I ready to talk about the bonus yet?
Not q then not q.
Well, we'll get there. I still have some more examples for direct proofs, I think. So let's continue with direct proofs. The bonus actually introduced the contrapositive, and I'm going to talk about that in a little bit. So let's continue. Chapter 3. So we proved about odd and even lower. Trivial and vacuous. And I think we got that one. I don't think we did that example. Let's just do a couple more examples for direct proofs, just to make sure we have it down. Yeah, that's the claim. Let's talk about proof. How do we prove that? Right, we need cases. There are two cases to consider. One, x and y are both even, or two, x and y are both odd. How about case one? Assume x and y are even. Then what can we say? X equals 2k, y equals 2l, something else, where k and l are integers. Then you can say that x minus y would be equal to 2k minus 2l equals 2k minus l, and x plus y is equal to 2k plus 2l equals to 2k plus l. And since k minus l and k plus l are integers, we have the desired result. Okay. So this was one by cases because we talk about having the same parity, but there are two parities that you could possibly have, so you have to consider the case for both. And we are not done. We didn't do odd. Right? It's not a without loss of generality problem because being odd and even is sufficiently different. Adding a plus one would change what happens here. So you have to actually talk about that. Assume x and y are odd. Then you can say x is equal to 2k plus 1, y is equal to 2l plus 1. For k and l integers. Then you can say x minus y would just be 2k plus 1 minus 2l plus 1 is equal to, again, 2 times k minus l. And x plus y.
Since, minus y is going to be plus y for some integer.
If you formulate it that way, sure. If you think of like x minus y as just x plus a minus y, you could do that. And just say, we're just introducing another integer, which is the negative of y, and then what we said for plus applies here. Rudin would do something like that, but you should probably, at least here, I'd like to flesh that out. I'm not sure if one of your classmates were reading that, they'd catch that without you actually mentioning it. But let's say since k minus l and k plus l plus 1 are integers, we have the desired result. And then we can say the claim holds in all cases. So that was a direct proof by cases. How do you prove that? Well, assume n is an integer would be a good start.
Yeah.
Then what?
Try cases again. And odd. Or
Cases again, okay? There are two cases. N is even, or 2, n is odd. Okay? What about case 1? If n is even, then I can say n is equal to 2k, for k an integer. And so I would have n cubed minus n would be 2k cubed minus 2k.
So you pull out 2.
Which would be what we need 4k cubed minus k. It's 2 if n is odd. N is equal to 2k plus 1 for k an integer. And so if I take n cubed minus n, what would I end up with here? So with 2k plus 1 cubed minus 2k plus 1. What does that become?
I wonder if we pull out the n first, would it kind of simplify it? Because then you have n squared minus 1. N squared is always going to be odd, and then minus 1. So n squared can be expressed as...
Well, we can do that here as well. So pull out the 2k plus 1
Yeah.
times, and here we have 2k plus 1 cubed minus 1
Squared.
squared. Yeah, you have to remember algebra. Can't get away from it, algebra forever. Okay, so now what's your argument?
So then...
We could actually multiply this out and write it in a nice form, but there's actually a more elegant
So
argument.
if 2k, here you have 2k, well, only one case really. Because 2k plus 1 squared is going to be odd.
Right.
Therefore, you're
2k plus 1 squared is odd,
so
and since the difference of odd integers is odd, 2k plus 1 squared minus 1 is odd.
even.
Is even, is what we wanted to say. This is even. This means that 2k plus 1 times 2k plus 1 squared minus 1 is even, since it is an odd times integer. And that is that case. So you could do the algebra, just multiply everything out. If you remember the how to cube a binomial, which you know a plus b cubed is a cubed plus 3ab plus.
Shouldn't that be the difference of odd integers and
Yeah.
The difference,
Yeah.
I scratched out the wrong odd. I should have scratched out this one. Okay, hold on. Moving too fast. The difference of odd integers is even. That's correct. We proved that on last class. Difference of odd integers is even. Then this is even. So this is even because it's an odd integer, right, times an even integer. Because this guy here is odd, this guy here is even. Difference of odds is even, and then odd is odd. Even times odd is even. So overall we get even, which was what we wanted to show. Yes.
I was wondering, could you have factored n cubed minus n in the beginning to get n minus 1 times n plus 1? And then say that if any of them is even,
Oh, let's say, so you want to do n
cubed minus n is equal to n minus 1 times n, n times n minus 1 times n plus 1.
Okay.
And then, since at least one of them has to be even, the whole thing is even.
Right. How do you know at least one has to be even?
Because since it's alternating, it will be either odd, even odd, or even odd, even.
Right. So these are, well, what you'd want to say is these are 3 consecutive integers. Right? This is the first, this is the smallest. Let me write that out. Alternatively, note, if I take n cubed minus n, this is n minus 1 times n plus 1. These are this is the product of 3 consecutive integers. So at least one must be even. No dominant participles here. Because you know, once you take an even integer times any integer, the result is even. We also prove that. So you can have something like this, which is a very nice proof. I like this one a lot, actually. More than one way to skin a cat, as I said. And there's yet another proof where someone who just brute force through the algebra, it actually wouldn't be that bad to do that. And you can get to the answer that way. So this is a way that deals with cases. This way you actually didn't have to consider case. No matter what the cases are, you have to have at least one even integer in a list of 3 consecutive integers. So that's a nice proof. Let's do see what you guys come up with this one. This is sort of a segment. This is just in case you missed it. Okay, for non-negative integers, 2 to the n plus 6 to the n is always even. How would you prove that?
So you can pull up well, first off, if n is a non-negative integer, then 2 to the n and 6 to the n are both going to be integers.
Yes.
And then you can pull 2 up.
Assume n is in this set, then you want to pull the 2 out?
Yeah, so it'd be 2 times 2 to the n minus 1, and 2 times 3 times 6 to the n minus 1.
And 6 to the n is equal to
2 times 3 times 6 to the n minus
2 times 3.
1.
What do you want to do?
No, well, yeah, you can do that part.
Hmm?
Yeah.
2 times 3. You said 2 times 3 times 6?
Yeah.
You factor out a 6. Okay.
Yeah.
What's 2 times 3? Yeah, you actually factor out a 6, but you said you
Yeah.
wrote it as 2 times 3. Okay.
Yeah. And then you can pull 2 out both.
And how do you know these guys are integers?
No, that's okay.
It's going to work if you take 2 cases, n equals 0 and n is a natural number.
Right. So I know what you want to say. You can write as 2 times an integer, but the thing is 2 to the n minus 1 is not always an integer
So
here.
n is 0.
So this is
So you
one
can
where you
do
have some cases. So now you can say
n is greater.
we have cases 1, n is 0, or 2, n is greater than 0. In the first case, you just literally just plug it in. If n equals 0, then 2 to the n plus 6 to the n is just 2 to the 0 plus 6 to the 0 equals 2, which is even. And in case 2, n greater than 0, then 2 to the n plus 6 to the n is equal to 2 times here, 2 to the n minus 1, plus 3 times 6 to the n minus 1, which is even, since 2 to the n minus 1 plus 3 times 6 to the n minus 1 is an integer. So if I asked you to show that this is equivalent to that, how would you do it? Truth table, simple enough. So P, Q, P implies Q. Not P, not Q. Not Q implies not P. So here I have true, false, true, false, true, true, false, false. P implies Q is only false when P is true and Q is false. Which is how we know what the negation is, right? If P is true and Q is false, that's the only time it's false. So the negation of this is actually P and not Q. So, not P, false, false, true, true, false, true, false, true. And so the only time this would be true, false, is if this is true, but that is false. So it's false here, but it's true everywhere else. And we notice from here, these two are the same, so we have equivalence. Which brings us to the next proof technique, which is the proof by contrapositive. I did mention that. We did do a few examples of that later on. In last class, I think. So. I don't think there was much more to say about it.
Okay.
So, without loss of generality is just when you have cases, but two or more cases are similar enough where it's just a waste of time to write down.
Okay.
That's basically the idea.
So do you have to do at least two and then write without loss of generality?
No, it varies. Just whenever several cases are the same, you can say without loss of generality. So, for example, if I say something like x and y are even, just a silly example, it implies that x plus y is even, right? Or,
Or they have the same,
let's say,
or if they have the opposite parity,
Opposite period.
then they're odd. The sum's odd.
let's say you wanted to do something like that. Then you could say, that's the without loss of generality proof. Because then, no, that's not something we use. Yeah, parity is what
You
we
could say
want.
if just x is even, and you have y, then x plus 2y is even.
That would also not be in the loss of generality though.
Because then you have,
Yeah, how about the one that we had before? So if x and, you mentioned it earlier, are odd.
if they have opposite parity, then
That one where we talk about x minus y was even. Would that be sufficiently good for a loss of generality proof?
I guess my question is like, when does it become a with loss of generality?
Yeah. I'm trying to give you a nice example for one. That's not just
yeah.
too straightforward or stupid. Okay.
Can you say that, for example, if x and y have different, one
X
is odd and
y
one is even?
Have opposite parity,
Yes.
then what?
Then x plus y is odd.
Did we prove that before?
I think those
Yeah. I think that was what we.
That was the example I used.
Yeah, that one.
So, so here, this is a without loss of generality proof, because you realize there are really two cases here. You can have case one, where you say x is odd and y is even, right? Or you could have case two, x is even, but y is odd, right? And if you were to write out this case, what you would say is something like, x is 2k plus 1, and y is 2l, and so you can say x plus y is equal to 2k plus 1 plus 2l, and this would be 2 of k plus l plus 1, which is odd. Now the thing is, if you come over here, what you could have done is say y equals 2k plus 1 and x equals 2l, and then you'd have x plus y would essentially be 2l plus 2k plus 1, which is 2 times k plus l plus 1, which is odd.
Isn't that just cases though? What
And you'd see here, so this is case 2.
Yeah.
You'd see here that this part of the proof and that part of the proof, which is really the bulk of it,
Yeah.
it's essentially the same thing.
So
I would literally essentially copied stuff down. Like switching x and y didn't matter.
yeah.
Like if one was odd and one was even, or oh, what if the other one's odd and the other one's even? It's the same thing, right? So in this case, you wouldn't do this. You'd say, there are two cases, this and that, but without loss of generality, consider this.
But there are cases where, you know, it goes beyond just the two cases that.
Yes, there are cases where you can have 4 or more cases, and maybe 2 of them you could do without loss of generality. But you need to make sure when you use loss of generality, the cases that you omit are really essentially the same thing. I'm pretty sure your homework you have problems like that where it has like 4 cases, but you can avoid doing all 4. You can only do like 2 or 3 cases to cover everything.
So you would just do, it depends on the problem, so you would do 2 and then.
It depends on the problem. You have to make sure that one is really similar to the other, and so you can read it out. But it's really just a trick to avoid writing down and stuff that really doesn't help. You're essentially going to be copying the same proof twice. You use it without loss of generality. That's essentially what it's about. That's pretty much the only place you use it, sort of. When there are several cases, but the cases are similar enough that you can omit one or several. Right? You use it without loss of generality. I believe your homework has an entire section on it. And the book has a lot more problems than I assigned for homework, so you can practice more if you'd like. I really want to at least talk about proof by contrapositive here, which is another proof technique. And I'm going to sort of tell you when you want to use it. First, let's know how it works. So this really takes advantage of the fact that we just proved by the truth table that these two guys, these two statements are actually equivalent in all instances. They give us the same truth values. You can essentially prove one by proving the other one. So again, like a list of steps you want to take that tell you everything but nothing, is the first thing you want to do in a proof by contrapositive is to assume Q is false. Or, in logical terms, assume not Q. And then your goal then becomes show that P is false as a consequence. And that's basically the idea. If you can show that not Q gives not P as a consequence, it's the same thing as proving P implies Q. So, sort of, let me just mention this first. Direct proof versus proof by contrapositive. So basically, rule of thumb, if you're deciding which to use, do what makes your life easier, that's basically it. That's not general advice just for when you're choosing between these two. Do what makes your life easier. Notice that in a direct proof, you assume P, whereas in a contrapositive proof, you actually assume not Q. And the question is, what you want to ask yourself when deciding between these two is, which of these statements is easier to deal with? right? That is something like they might have less cases or makes the rest of the code easier, right? So basically, start with what you know you have to assume. You know, if you're a direct proof, you have to assume P. And if you have a contrapositive proof, you will assume not Q. One might be more difficult than the other. So,
But is it possible that it can be done regardless, or?
it will usually
Not be?
not be. At least not in the cases that we'll be looking at. But technically. So, example. If 5x plus 3 is odd, then x is even. Okay. So what you notice here is that this guy here is your P, this guy here is your Q. Now if you're looking at this and you're thinking, do I want to do a direct proof or a proof by contrapositive? And you're trying to choose between the two. Saying that this expression is odd is a lot more difficult than just saying x is odd, right? So if you do something like, assume 5x plus 3 is odd. Well, what does that mean? Well, it means that 5x plus 3 would be equal to 2k plus 1 for some integer, right?
And then,
So then, if you want to figure out what x is, you're going to, well, solve for x, right? So you're going to be like, well, x would be, in this case, 2k minus 2 over 5. And then you're going to be like, is that an integer, right? And that's sort of hard to tell. The top is even, and you're dividing by an odd integer, which means that this has to be a multiple of 5 for you to know it's an integer. It's sort of, yeah.
For the bonus on the quiz just now,
Yes.
there was something like this, but if we kept it as 5x, well, in a case like this, if we kept it as 5x equals 2k minus 2, and said that 5x is even, and if you divide an even integer by any number, it's even also. Can you say that x is even?
If you divide an even integer by
Any integer. By 5 in this case.
So if you're dividing like 10 by 2, you get 5, which is not an
No, I mean divide by 5.
So you want to say if you divide any even integer by 5,
Well,
That's-
that would be.
that wouldn't be
put it
true.
that way.
it would be,
If you want to do that, you'd say something like, well, 5x is a product of an odd and an even. Well, it's a product of two integers, one of which is 5. If you get an even, then one has to be even, whereas it's still kind of sticky. And we are going to talk about divisibility of integers, so you'll sort of see why. Because an argument like that, to be really pedantic, you have to take advantage of the fact that 5 is a prime number, right? There are cases where the thing you're multiplying by, if it's not prime, there will be like issues. But essentially you can see here, if you do this, sort of arguing around that is sort of going to be sticky. If you try to solve for x directly, you get this thing, I don't know if that's an integer. You can't be sure, you can't know. You won't convince someone this is an integer, right? And to argue the other way, then you're gonna be like, well, 5 times this is even. It must mean that x must be even because we know that 5 is odd. There are other sticky situations that will not get figured out as well. In any case, the point is, and again, this is a simple example. In the real world, in real life, you'd be working with much more complicated things than this. But even with this simple example, you can see it's already a little bit hairy trying to approach it the direct way. Whereas a assuming x is odd is really easy to deal with in comparison. So something like this, you'd say, assume x is odd. Then we know where to go with this. X is 2k plus 1 for k an integer, which would mean that 5x plus 3 is, now I just plug that guy in here. So that would just be 2 times 5k plus 4. Right? And right now, there's no like argument. This is an integer, right? There's no division going on. So since 5x plus 3 is odd. And then you can go like the So essentially what we did was we assumed, this is actually assuming not q, and we got the result.
Even is what
It's even is what I'm mixing up odd and even. Not p. Right? It's 2 times an integer, so this is even. Right? So I assume not q, and then I showed through, as a consequence of that, I get not p. So what I actually showed is that not q implies not p, which is the same as showing p implies q, and so this holds by the contrapositive. And I would have chosen the contrapositive because dealing with just x is odd is a lot easier than dealing with this is odd. Another example. So any questions on this so far, or do you sort of see where you might choose one over the other? Right. So basically, if your first statement is complicated and the second one is simple, you choose the contrapositive. If the first one is simple, the second one is sort of complicated, do the derivative. It's basically the idea, make your life easier. That's basically it. We are going to use this later, so let's just deal with it. Claim is x, let x be an integer. And x squared is even if x is even. And like I said, I know how to spell the word if when I do that. It actually means something. So remember what if with 2 f's means? If and only if means there's a by implication to prove. So whenever you see that, or the phrase if and only if, you actually have to prove an implication in both directions. So how we usually do that is you break it up. Customarily, you like put one of the arrows in brackets. Like in shorthand, this is usually what we do. So you choose which one you want to prove. Which way you think is easier to prove? That way, right? So you put that in arrows and you put a colon. Right? So you sort of hint to the reader which direction you're going to be working on. So I'll just put in brackets this guy, right? And so now, so essentially we show if x is even, then x squared is even. This sort of screams out direct proofs at us. The first statement is pretty easy to deal with. X is even. x squared is even would be worse to deal with, because if I said x squared even, I'd say x squared is equal to 2k, and then to get to x, I'll have to take a radical. I'd have a radical 2 times a radical k, like who knows if that's an integer, right? So directly, assume x is even, then x would be 2k for some k in integers. This means that x squared is actually equal to 2k squared, which is equal to 2 times 2k squared, which is even since 2k squared is an integer. And now you say, okay, now we want to go this way. And if we're doing that way, what would we want to do? In other words, we want to show if x squared is even, implies x is even.
So do the contrapositive.
In this way, I do the contrapositive for the same reason I mentioned before. Assuming this directly, I assume x squared is even. How would I have to get to x? I'd have to like take a square root, which that could mean anything, right? So in this case, the first statement is more complicated to deal with. The second statement, though, is pretty easy. Even its negation is pretty easy to deal with. So in this case, I would assume the contrapositive. So So we will assume the opposite of the second statement, assume x is odd. And my goal now is to prove that x squared would also be odd. So if x is odd, then I have x is equal to 2k plus 1 for k an integer. And so I would have x squared would be 2k plus 1 squared, which is 4k squared plus 4k plus 1, which is 2 times 2k squared plus 2k plus 1. Which is odd, since the 2k squared plus 2k is an integer. So saying here, I'm assuming by way of contrapositive, it hints to the reader that you want to end up with x squared being odd, not being true. And right here I've proven that it's odd. So that gives us that. There's a very nice proof by contradiction where we're going to use that fact pretty soon. How about this example? If 3x plus 1 is odd, then 5x plus 2 is even. And as I said here, we're going to use a lemma, right? And sort of see here, I introduced what a lemma was at the beginning of this chapter. Let's sort of see one in action, like how this lemma would work. How a lemma works. So remember what a lemma is. It's sort of a smaller theorem that helps you prove a bigger theorem. And you can sort of, once you've proven a lemma or it's been proven somewhere, you can always just quote it and use the result that it gives you. So how do we go about this? So now you see a problem like this, and now you're like between a rock and a hard place. You're like, well, This one is sort of complicated, and that one is sort of complicated. There's no one statement here that's sort of more easier to deal with than the other one. So you're like, direct proof, contrapositive, not sure. So you might decide, okay, let's do the direct way. Let's start with this. But how do you actually get to it?
So that 3x plus 1 implies that x is even.
That would be another way. So let's say here, so what you would do is you do a lemma. So you make another claim. 3x plus 1 is odd would imply that x is even. Right? Now, why would you think of saying something like that? Well, to sort of tackle it, you sort of thought as, I need to learn your names. I don't, what's your name? Chris. Yeah, as Chris was mentioning how we're playing around with what we know about multiplication of integers. Well, you sort of look at this and you're like, well, this is an odd number and I'm adding it to this guy. If I know the sum of two integers is odd and one is odd, it must mean the other one has to be even, right? So if 3x is even, I sort of know that the x has to be even, right? And so you're like, well, maybe this factor will help me out. This is a much easier statement to deal with, so if I can get that in there somehow, that will probably help me out. So you start with a lemma. Let's say this is an assumption you make, and we're going to hope that it's true, but we of course don't work on hope, we work on proofs. So you do proof of the lemma. How do you prove this lemma? Contrapositive. Again, dealing with this directly is sort of difficult, right? So you want to even avoid that. Let's start with this guy. By the contrapositive. Assume x is odd. Then x is equal to 2k plus 1 for some integer k, which basically means that 3x plus 1 would be equal to 3 times 2k plus 1 plus 1, which would be equal to 2 times 3k plus 2, which is, of course, even, right? Now, usually when you're proving a lemma, you draw a box, but you don't shade it in, right? Sort of to indicate that, oh, this is a little proof that we're doing. Yes?
I thought lemmas were already proven true from before.
Not always. It could be. It's possible, right? It's possible to use a lemma that someone has proven somewhere, and then in your proof, what you'd say, using the proof from this source as a lemma, we continue blah, blah, blah. But it's possible that sometimes you have to invent your own little theorem, right? So a lot of times it comes down to proving something big. You break it into smaller chunks, and you prove little things along the way to help you to get to something bigger. So now, what we've done is we've proven a lemma, and we're actually going to use this to prove this entire claim. Right? So we now prove 3x plus 1 is odd, implies 5x plus 2 is even. And let's do it directly now. So assume 3x plus 1 is odd. Okay. So we're not going to be like 3x plus 1 equals 2k plus 1. It wouldn't really get us anywhere nice. But we can say then, by the lemma above, we have x is even. Since x is even, x equals 2k for some integer k, and that would therefore mean that 5x plus 2 would actually be 5 times 2k plus 2, which is actually 2 times 5k plus 1, which is even, since last example for chapter 3. So we completed chapter 3. But again, this is a small playing in the sandbox kind of example of where you might use lemmas to help you out. So you have a proof, but sort of both statements are sort of incontractable. You don't really know. Neither one is really easier to assume rather than the other. And usually if I assume one or the other, I'll get like fractions where I don't know if it's odd or even. So what you do is you sort of use an educated intuition sort of that you have to make some sort of other smaller claims about these numbers. So I can sort of make the claim, well, if I know this is odd, what do I actually know about x? Because we've known from previous experience, just deal with x by itself seems to work out usually. So if I know this, can I say anything about x? And then we sort of know, well, I'm adding an odd integer to another integer, and this, to get an odd, I must have that must be even, right? Because we've proven that, right? You have to have different parities for when you add them, you get odd.
Could we,
What?
would it be possible to choose different lemma to say like 5x plus 2 is even implies that x is odd or even?
Yeah. Well, you could. Yeah, x would have to be even. You could do that. So then.
And then what is how would that work?
Then you can just do a contrapositive.
Then you're doing contrapositive. Like you have a contrapositive within a contrapositive. Exactly. So you could have done that lemma, but then, as he said, it doesn't make our lives easier to do that because we'd have to do like 2 contrapositives. Because then I'd have to assume the negation of this, which makes it odd, which means I have to assume the negation of my lemma, the contrapositive of my lemma to use that, right? So.
Are there cases in which that would have to happen though? So like you would have to do like a double contrapositive.
Well, if this statement is really complicated, that you don't want to deal with it even in a lemma,
Right.
then that might be an option. So yeah, it's really, so like I said, there's no hard and fast, we always do this. It's not like a quadratic formula kind of thing we're doing anymore. So, yeah.
If by chance that statement said like if 2x plus 1 is odd, then whatever, which you could have skipped the whole lemma, right?
If it said 2x plus 1 is odd,
Yeah.
how would you skip the whole lemma?
Because you would.
Because telling you 2x plus 1 is odd is sort of like telling you nothing. Right?
Yeah.
Obviously 2x plus 1 is odd. And you sort of have to just prove that this is even. How would you skip the lemma? What would you say if you wanted to skip it?
Would you just say like since any integer 2k plus 1 and then you would say x equals k? Because the definition of an odd number is 2k plus 1. And if you have something that says if 2x plus 1 is odd.
So you have if you have 2x plus 1 equals 2l plus 1.
Something like that. You could have skipped the lemma in that case.
Well, all you could conclude from that is that x equals l. Then you have to deal with cases. What if L is even? What if L is odd? Right? Because within this definition, there is no statement about the parity of this integer. Right? It's just, this is odd where X is any integer, some integer, right? It could be even or odd. So just saying that this is odd doesn't really help you with the X. The X could still go either way. It would still be odd overall. So. But yeah, so sometimes it's sort of obvious. You have like an implication where the first statement is easy, the second statement is complicated. You probably want to try a direct proof. Second statement is easy, the first one is complicated. You probably want to do a proof by contrapositive. But then there are cases where both statements are sort of weird. And so you sort of, again, tackle which one would make your life easier and try to fit a lemma in there somehow. Try to get a baby step, a half step in there, where you go from one to another mid step where that step is actually easier to get to the other one. And it might go both ways, but in this case, I think going from the direct way was better. So we sort of prove this gives that, gives this ultimately. And then this claim would be called a lemma, because it's a little proof, a little thing that you know is true that you use to help you prove something bigger. So that's sort of when a lemma might be useful, when sort of getting from one step to the other is just too difficult to do in one leap. stop there for now. That completes chapter 3, so the homework for that is due tomorrow. And